Okay, I hope the PPT is visible. Fine. So let's do a revision of the previous class. What we've learned in the previous class was about the different 2D geometric primitives as well as 2D geometric transformations, right? So for the 2D geometric primitives, what we saw was how can we mathematically represent different primitives such as points, lines, or conic in the homogeneous representation, that is in the projective space, right? So first we saw that for a point, okay, I can represent it. What I do is, this is for 2D, right? So for the homogeneous representation of the point, what I do is I just add in a third coordinate. Okay, so I can write it as, like, for example, if I'm taking the point as x1, I can just use different coordinates here, w or so. Okay, and we also saw that this would be equal to writing it as xy1 if we take this w as a scaling factor. So we can say that in the projective space, okay, it is defined up to a scale. That means when we are converting back to the non-homogeneous representation, what we do is we always divide by this third coordinate. So if I want to get in the non-homogeneous representation, if I want to get the same point, I can write it as x1 is equal to, now the points become x by w and y by w over here. Okay, so it's always defined up to a scaling factor or a scale. Now this is a representation for a point. Next, what we saw was for the line, how we can represent is, let's say you're taking a line L1, okay, I just write it as A comma B comma C, right? If the corresponding equation, what we are saying is the equation that it satisfies is ax plus by plus c is equal to 0, right? And we saw that, let's say if you have a point x, okay, and we are and to know or to check whether this point x lies on a line L1, let's say, okay, all that we need to do is we need to see if it satisfies the equation. Can anyone tell me what is the equation that it should satisfy? That is, if the point x lies on a line L, then how do you find that point x, or how do you know whether the point is exactly lying on the line? Okay, so we take the dot product, okay, of x and L, that is a point in the line. If I take x dot L is equal to 0, and if this equation is satisfied, I can say that this point lies on the line. So that is one thing we saw last time. Another point that we discussed was, let's say you're given two lines which are given by L1 and L2. Then if you want to find what is the point of intersection of these two lines, then all I need to do is I can just find the cross product of these two lines. Okay, so I can say the point of intersection, let's say if it is L, I can say that the point of X, then I can say the point of intersection that is X is given by L1 cross L2. So if I simply take the cross product of L1 and L2, what I get would be the point of intersection. Now similarly, let's say I'm considering 2 points x1 and x2, okay, and if I want to find the line which is passing through the points x1 and x2, then what I do is I can just write it as L is equal to x1 cross x2. So here also simply taking the cross product of the 2 points which is given to us, what we get would be the equation for the line. Okay, so all these are in homogeneous representation, and these were some of the points that we discussed. And the next primitive that we considered was the conic, right? And here also similarly, what we have discussed is that, let's say if there is a point x which is lying on a conic, then if it's satisfied, we can say that it satisfies the equation x transpose cx is equal to 0, where this c is what you call as the conic coefficient matrix, right? And we can represent this by, we had already seen what was the term that we used. Okay, so we have a, c and f, right? This is b by 2 here, b by 2 here, then d by 2 here, d by 2 here, and then here I have E by 2. Here also I have E by 2. Sorry, this should be here, this should be here, right? So what we saw again was that this is a symmetric matrix, okay? And these values A, C, F are basically the coefficients of x1 square, x2 square, and x3 square. If you're taking that x1, x2, x3 are the coordinates of the point, okay? And we also saw that when we take or express the unknowns over here, what we do is, since it is taken as ratios, okay, we can represent it as A is to B is to C is to D is to E is to F. So since it is ratios, the total number of unknowns that we find over here are only 5. That means we need minimum 5 points to define or represent the particular conic. Okay. So this was regarding the 2D geometric primitives. Then coming to 2D geometric transformations, can anyone tell me what are some of the 2D geometric transformations that we discussed last class? Just the names? Yes. Okay, so first we started off with translation, right? So when I say translation, what that means is, let's say I have an image or an object, right? Or let's take an image itself, right? And all that you do is, when it is translating, let's say along the x-axis or along the y-axis or both, okay? So translation is basically when the shape of the object, okay, remains the same, the whole shape remains the same. It's just that the coordinates with which it is represented, that only changes. So I can write it, let's say if x is a point, okay, and x dash is the transformed point, then I can write x dash is equal to x plus t, okay. Or if I'm writing this in terms of in a matrix form, I can also write this as x dash is equal to, what we have here is the identity matrix, which is a 2 cross 2 matrix. Then I have T, basically this is Tx and Ty, okay, so it's a 2 cross 1 matrix over here. Then I have a 0 transpose and 1, right, and X. So this is my transformation matrix for a translation operation, okay. And the unknowns that I have is Tx and Ty, so the degree of freedom here is 2. And we see that translation always preserves the whole shape, okay, of the object. Now, after this, what we discussed was about the rotation along with the translation. So it was rotation plus translation. So in the case of rotation, what we have is we use, or we are introducing a rotation matrix, right? So therefore, I can write it as x dash is equal to a rotation matrix, then space small t here and x. So here the t represents tx and ty, which is a translation along the x direction and y direction. And R is a matrix over here, which is given, or which is in terms of theta, right? And we saw that if we are trying to represent this in the homogeneous representation, how we can write this is x dash is equal to, the only difference is, can anyone tell me what is how the matrix would look like when I'm adding rotation along with the translation? Okay, so this was the transformation matrix for a translation. How would the transformation matrix look like when you are adding in a rotation? Okay, so the only difference here is that on the only thing what you do is you have a rotation matrix. So we are replacing the identity matrix which you're using here with the rotation matrix. Okay, so there's a rotation matrix, 0 transpose T and 1. This is the only difference that you have. Okay, now one thing you have to remember is, so the difference is that we are replacing the identity matrix, 2 cross 2 identity matrix, with the rotation matrix. And this rotation matrix, it has got some constraints. That is, this should be, you cannot take any 2 cross 2 matrix as a rotation matrix. It has to be an orthonormal matrix. So this is something we saw last time. Then the next case that we discussed was if along with rotation and translation, we are also adding in a scaling, okay? Can anyone tell me, when you have rotation, transformation, and scaling operations together, what do you call that particular space or the geometry? Like for example, when you have rotation and translation together, you call that as a Euclidean space or the Euclidean geometry, or it is basically Euclidean transformations, right? So when you have rotation translation along with that scaling, what do you call this particular geometry? Okay, it is called as the similarity transformation, or you call as a similarity space. Okay, so when you have rotation, translation, and scaling, the only difference you have is that there would be a scaling factor which you're using. Okay, a non-zero scaling factor. So how I can write this is I can write x dash is equal to, now this becomes small s r plus no, plus t, because this is a matrix form. I write it as SR space t, okay, and then I have x, right? So all that you're doing is you're taking first a scaled and rotated version of x and then translating it, okay. Next, what we have is the affine transformation. So for the affine transformation, what you have is that includes the rotation, translation, scaling, stretching, linear stretching, shearing, etc. So all these operations together combine the affine transformation. And in affine transformation, what the property which is preserved, the property of that space which is invariant is the parallelism. Okay, so the parallelism is preserved in the affine transformation or in the affine space. And the equation how we write here is we just take it as x dash is equal to ax, right? And this A over here, it is basically a 2 cross 3 matrix. When we are taking a homogeneous representation, A is a 2 cross 3 matrix. And you can take any arbitrary 2 cross 3 matrix as the affine transformation matrix. And then finally, you have the projective transformation. So in the projective transformation, the general equation can be written as x dash is equal to hx, where h is a 3 cross 3 matrix, and here also any arbitrary 3 cross 3 matrix can be used as the projective transformation matrix, or h, which is given over here, right? And the only property, can anyone tell me what is the property which is preserved in the projective space? Is it lines? Is it angles? Is it parallelism? What is preserved, or what is the property which is invariant? No one? Okay, Achintya, if you're there, can you tell me what is the property which is preserved in the projective space? Or if anyone can't unmute, can you write it in the chat box? For affine space, what is the property which is preserved? I just told now. I want some answer. Anyone? The question is, what is the property which is preserved in the affine space? Okay, Pratik Shetty, you have replied that in the projective transformation, the lines are lines, basically the straightness is preserved. Very good, and thank you, Pratik, for responding. Okay, so I'll go forward with the class. Let's go to 3D geometric primitive and 3D transformations. So if you've understood the 2D registration transformations as well as the 2D geometric primitives, it would be easy for you to understand the 3D geometric primitives as well as the 3D transformations. Okay, so in the case of a 3D space, right? What we are assuming here is that, so first we'll be just going through what are the different mathematical models which are used to represent the various 3D geometric primitives. Okay, so we'll take the case of a point, a plane, a line, etc., and how we represent that in the 3D space. Okay, and one point you have to remember is that when you are considering in a 2D space, there is a single plane. We assume that if you have any two lines, it will always intersect at some point, right? In the case of 3D space, what we see is, like, for example, the example which is shown over here, what we see is that, like, for example, in these two lines, right, when you're taking a projection, a 2D projection of these two lines, okay, what we'll see it as an intersecting a pair of intersecting lines. But when we look at the 3D view over here, we can see that okay, these lines basically lie on two parallel planes. Okay, so that means it does not really intersect, even though the 2D projection shows that. So what we can say is that we cannot always say that the two lines or any two pairs of lines would intersect, okay, in a 3D space, because sometimes the lines may be, even though the orientations are different, okay, they may be in two different planes and therefore they may not intersect. Okay, so because of that, there would be some changes in the different mathematical representations or the algorithms. Okay, now coming to a point. How do you represent a point in a 3D space? Okay, so in the case of 2D, we saw that how many coordinates do you use to represent a point in 2D? How many coordinates do you require in the homogeneous representation? Okay, fine. So in the homogeneous representation, what we say is, let's say it is a 2D space. If it is a 2D space, then we can say, let's say I have a point X, right? I can represent it by just three different coordinates if it's a 2D space in a homogeneous representation. So I'm just repeating what I've said earlier, that is, in the homogeneous space or in the homogeneous representation, what we do is we are adding in an extra coordinate over here. Okay, so in the non-homogeneous form, what we have is, let's say you're taking a point in 2D space, you have only two coordinates, for example x, y, let's say, right? But in the case of homogeneous representation, we always add in a third coordinate as the last coordinate. Okay, and to convert from this homogeneous representation to the non-homogeneous representation, what we do is we divide by this last coordinate, right? Now, if it is a 3D space, what we do is, to represent a point, again, we add in another coordinate. Okay, so that would be a fourth coordinate. So originally in the non-homogeneous representation, you need only three coordinates to represent a point, that is x, y, z, along the x, y, z axis, right? In the homogeneous representation, we add in a fourth coordinate, okay, and let's call that an x4, right? Now, if this coordinate x4 is equal to 0, right? It is not supposed to be equal to 0, or the last coordinate, right? So if it is equal to 0, like for example, let's say over here, if this is equal to 0, if I get some values of x1 and x2, and if it is equal to 0 over here, what can I say about this point? Where would be the location of this point? this point would be located at infinity. See, this is the basic use of using this homogeneous representation. Okay, homogeneous representation is used only so that we can have a specific notation for the point at infinity, and how we represent that is when a point has got the last coordinate as 0, then that means that that point is at infinity. So similarly in this case also, when you're taking the point in 3D space, what we have is 4 different coordinates. And if the fourth coordinate is a 0, then that means that it is a point at infinity. So the same principles that we have learned in the 2D space also applies to the 3D space. Okay. The only thing is that you'll have this extra dimension, that's all. Right. So if I have to convert this to the non-homogeneous representation, what I do is I divide by the last coordinate. So my if x, y, z are the 3 coordinates in the non-homogeneous representation, to get back this non-homogeneous representation from the homogeneous representation or homogeneous form, what I do is I just divide by the last coordinate. So I have x1 by 4 here, x2 by 4 here, and x3 by 4 here. Okay. Now, coming to projective transformation, right? So I can represent projective transformation by x dash is equal to hx. This is an equation that we already saw in the previous class for a 2D case, right? So if it is a two-dimensional space, we saw that when you're writing x dash is equal to hx, okay, these x would be having only 3 dimensions. So what I have here, this h would be a 3 cross 3 matrix if it is in 2D space. Okay. Now, since it is 3D space, for x and x dash, I have 4 coordinates, right? That is basically x1, x2, x3, x4, which is already written here. So since there are 4 coordinates for this transformation matrix, which I'm using H, okay, it would also be a 4 cross 4 matrix. So even though if it's a 4 cross 4 matrix, so let's say it starts from H11, okay, and I have till H14 here, and here I have H41, and I'm writing all this, and then I have H44 here, right? So totally it should give you 16 elements in the matrix H, okay? But when you're calculating the total number of unknowns over here, it won't be 16, it would be 16 minus 1 is equal to 15, because because here this h44 becomes a scaling factor, right? And we can divide this all the other elements by h44 when we are converting to the non-homogeneous form. Okay, so that means in effect the number of unknown ratios which I'm calculating is just 15. Right, so my degree of freedom in the case of the 3D space for H or the projective transformation matrix would be 15. Okay, so next let's see how we can represent planes in the 3D space. Okay, so it is very similar to how we represent lines in 2D space, right? So lines, as I said earlier, how we represent is, I write it as this way: if I have ax plus by plus c is equal to 0, right? Now, in the case of planes in a 3D space, right, it has got the coordinates which I have is x, y, and z, okay, and the different coefficients which I have is pi 1, pi 2, pi 3, and pi 4. So the equation is basically written this way, that is pi 1 x plus pi 2 y plus pi 3 z plus pi 4 is equal to 0. Okay. Now, just like the line in the 2D space, okay, we can say that for a plane in the 3D space, we can represent this as a homogeneous equation, okay, and the homogeneous representation can be written this way. That is, I write a bracket pi 1, comma pi 2, comma pi 3, comma pi 4, okay. So it would be a 4-vector form over here, just like how you have the line in 2D space. This is how we write the plane, the equation for the plane in homogeneous representation in 3D, right? Now, the degree of freedom over here just like again in the previous case, this pi4, okay, that's a scaling factor. That means I represent these unknowns as ratios. When I'm representing it as ratios, I write it this way: pi1 is to pi2 is to pi3 is to pi4, and therefore the total number of effective unknowns which I have here is 3. So therefore the degree of freedom what you have for a plane in 3D space is 3. Now, in the 2D space, okay, if there is a point X which lies on a line, as I said earlier, all that you do is we take the cross product, I mean the dot product of these two to see whether the point lies on the line, right? So a similar concept here, what we do is if we want to say, let's say X is a point, okay, and pi is the plane that we are considering. And if I want to see whether this point X lies on the plane pi here, what I do is I just compute the dot product of these two quantities, okay, or these two vectors, or all that I do is in matrix form, I can write it as pi transpose X is equal to 0. So if this equation is satisfied, then I can say that this particular point X lies on the plane pi. Okay. Now, for the non-homogeneous representation, we have already seen non-homogeneous representation can be pi1 x1 plus pi1 x1 plus pi2 x2 plus pi3 x3 plus pi4 x4 is equal to 0, right? So you can represent this way. Now this equation, you can also rewrite that, or another form of representing this is this equation which is given over here. That is, I can write it as n dot x plus d is equal to 0, okay, where n is given by n is equal to pi1, pi2, pi3. Okay, so this is basically when I say pi1, pi2, pi3, what that means is, let's say you're considering a particular plane, okay, and this n is basically the normal to the plane, okay. So when I take the coefficients of pi1, pi2, pi3, okay, that gives me the value n, or the normal. Then x1, x2, x3, they are basically the coordinates of the point x, okay, and the x4, or basically this x represents these coordinates x1, x2, x3, and then x4 you can take that as 1 over here, okay, to get this particular equation, and d is nothing but pi4, okay. And this gives me or this is just another way of representing the non-homogeneous representation, okay, for a particular plane. Okay. So now there are certain properties of planes that you will have to note in the 3D space. So the first property is that when you're looking at the equation of a plane, right? So you need at least 3 points, okay, 3 non-collinear points to find the equation of a plane, right? So that is the first point. Another point is that two distinct planes always intersect in a unique line, okay, and that is shown in this particular figure here. That is, let's say you're assuming two planes, you have plane 1 here and plane 2 here, right? And if you look at the intersection, okay, between these two planes, what you see is a line, okay. So if I take any two distinct planes, I always see, or what I can observe is that it will always intersect at a line, okay. And similarly, if I'm taking a third plane, okay, so if I taking a third plane, three distinct planes, what I see is the point of, there would be a point of intersection. So basically all these three planes would always intersect at a unique point, which is shown over here, okay. Now, let's say there are 3 points or 3 planes which are given by pi1, pi2, and pi3. So let's say these 3 planes are given by pi1, pi2, and pi3. Okay, these are not the coefficients, but these are 3 different planes. Okay, and you want to find the point of intersection of these 3 planes. So what we do is, just like how we discussed in the previous case, in the previous case, what we saw was, let's say you have a point X and you have a plane pi, then if you want to find whether this point lies on the plane, we saw that what we do is I just take pi transpose x is equal to 0. Okay, so similarly, if you have three planes and you want to find the point of intersection of these three planes, all that I do is I take the equations of these three planes. So that would be pi 1 transpose, pi 2 transpose, pi 3 transpose x is equal to 0. And the solution of this equation would give me what is the point of intersection of the three planes. Okay, now how do you represent lines in 3D space? So first what we discussed was how do you represent points in 3D space? Second is how do you represent planes in 3D space? Next we'll see how do you represent lines in 3D space. Okay. So we can represent, so as I said in the previous slide, okay, a line can be, it can be defined in terms of the intersection of two distinct planes, okay. So if I take two distinct planes, I can say their intersection will give me the line, okay. So if I'm defining the lines in terms of a plane, okay, and plane having three unknowns, there would be three degrees of freedom. So together for two planes together, there should have been six degrees of freedom, okay. But you can represent a line in just 4 degrees of freedom, okay. So in the sense, let's say you have two planes, plane 1 and plane 2, and the intersection of these two planes gives me this line of intersection over here, okay. So I can, what I'm saying is I can define this line in terms of these two planes, okay, or with respect to the equations of these two planes, okay. Now let's let me just assume that I am trying to rotate this plane, okay. So when I'm trying to rotate this plane about this line of intersection, which is seen over here, okay, we will get a different pair of plane, right? And for that different plane, pair of plane, again, the line of intersection is the same because it is being rotated along this line. So like that, each time when we try to rotate these two planes, okay, what I see is that the line of intersection would remain the same. Okay, so that means the line is actually present in all these planes, okay, which are considered right now, right? So that is, for all these planes, one set of parameters would always remain constant, or it would always remain the same. Okay, so in that case, I can represent the line of intersection, okay, using only two out of the three parameters in one plane, because since one parameter is always constant throughout, right, I can just remove that or not consider that parameter and just define in terms of the other parameters which are varying, okay, or which are not constant, okay. So therefore I have two parameters which I can consider from this plane and two parameters from the other planes. Therefore totally you have 4 degrees of freedom for a for representing a line in the 3D space, okay. Now there are different ways of how we can represent, or different ways by which you can mathematically write these lines, okay. We'll just look at two of these expressions. So one way in which you can write is, I can write it as r is equal to 1 minus lambda into p plus lambda q. Okay, so here I'm assuming that p and q are 2 points. Okay, and the line which is being defined by this equation is passing through these 2 points p and q. Okay, and this line is basically this r over here. Okay, and we are introducing another parameter or a variable lambda, okay, and by varying this lambda, what I get is the different points which lies along this particular line, okay. So like for example, if I take lambda is equal to 0 here, if this is equal to 0, the value of r which I get would be equal to p over here, because this would be 0. Now, if I take lambda is equal to 1, this term would go 0 and what I get would be here q, right? So that means when lambda is equal to 0, I get r is equal to p, and lambda is equal to 1, I get r is equal to q. So that means when I'm varying between 0 and 1, lambda, when I'm varying lambda between 0 and 1, what would be a line segment, right, which lies between p and q. Okay, and that is what this particular what expression or equation also represents. Now, there is a limitation for this particular equation. That is, what we are doing is we are actually introducing another parameter lambda, right? So we are actually increasing the degree of freedom over here, right? Because you are having this extra parameter again lambda, which has to be varied. So this is not a very convenient form of representation of a line. So a more convenient form that we usually use is known as the Plucker coordinates or the matrices. Okay, the Plucker coordinates, or it's called as the matrices. So how that is represented is, I write it as L is equal to PQ transpose minus QP transpose. And that is here also we assume that P and Q are basically any two points on the line. Okay, and given any two points on the line P and Q, right, what I can write it as L is equal to PQ transpose minus QP transpose. And here P and Q, it is given in or it is basically written as a matrix in the homogeneous representation. Okay, so this is a representation of line in the 3D space, and we call it as, this kind of representation is called as the Plucker coordinates and the Plucker matrices. Okay, now coming to 3D transformations. The 3D transformations are very similar to the 2D transformations. Okay, only thing is that for the 3D transformation, you will have the dimensions of the transformation matrices would be different, right? Because you have the presence of an extra coordinate in each of the points, right? So instead of 3 coordinates in the homogeneous representation in 2D space, it becomes 4 coordinates, right, in the 3D space in homogeneous representation. And so accordingly the matrix size also changes, but the basic principle or the basic way in which the mathematical model is built is the same. Okay, the equations are similar. So let's take the case of translation. In the case of translation, how I can write it as x dash is equal to x plus t, something which we have already discussed. But now in this case, the value or the dimension of x dash and x, okay, being the points, it becomes 4, okay, in 3D, because it is 3D space. Now we need 4 coordinates, x1, x2, x3, x4 to represent these points, right? So that means now you have this as 4 cross 1 and here also as 4 cross 1, right? And here t will have translation along the x direction, y direction, and z direction. Okay, so accordingly this also changes, and the identity matrix also becomes a 3 cross 3 matrix. In the case of 2D, it was 2 cross 2 matrix. Now here in this case it would be a 3 cross 3 identity matrix. So that is the only difference for a translation. Now, when you're considering both rotation as well as translation, just like in 2D space, what was done was we first rotate the coordinates of the points and then translate it, right? And this is how we write the matrix form, right? Now, in the case of 3D, what happens is the dimension changes. Instead of 2 cross 2, this becomes a 3 cross 3 rotation matrix. Okay, and the 3 cross 3 rotation matrix, it should have, it is just like in the case of 2D, where we say that the rotation matrix must be orthonormal. In this case, also in 3D space, also the 3 cross 3 matrix, which you are taking as a rotation matrix, should be orthonormal. Okay, so that property must be there. But here this r, okay, it is you cannot say that it is not a function of theta. I can say it is not a direct function of theta, in the sense if I go for a 2D space, just by using cos theta, sin theta, cos theta minus theta, sin theta, I can represent the rotation matrix, right? So all the elements in the rotation matrix is in terms of theta. So theta was the only unknown in the case of the 2D rotation matrix. But here in the 3D rotation matrix, which we are considering, it is not a straightforward calculation, and there is no specific parameter as theta which can be used to define the matrix. Okay, but having said that, the rotation matrix must be orthonormal. This basic property should be satisfied. Okay. Okay, now next is the scaled rotation. So in scaled rotation, what we are doing is we also add in a scaling factor. Okay, so there is a scaling factor along with rotation as well as translation. And the matrix is written in this form where you have x dash is equal to SR, T, and X here. Next is the affine transformation. So in the affine transformation, we saw that it was the same equation, right? In the 2D space, right? In the 2D space, what we saw is the size of the affine matrix is 2 cross 3, right? So any arbitrary 2 cross 3 matrix could be used as the affine transformation matrix in the case of 2D space. In the case of 3D space, we have one more element, right? So therefore, here now any arbitrary 3 cross 4 matrix can be used as the affine matrix. And finally, for the projective transformation, the equation, it is as shown over here, x dash is equal to hx, and the size of the matrix here, the projection matrix would be 4 cross 4 in the case of 3D. In the case of 2D, the size of h was just 3 cross 3, the dimensions. Okay. Here it is 4 cross 4, this becomes 4 cross 1, and this becomes 4 cross 1 over here. And we have this 4 because for a point in 3D space, to represent a point in 3D space in homogeneous representation, you will require 4 coordinates. Okay, and the basic property of the projective space is that it preserves the straight lines. So this is a summary of all the transformations, okay, the transformation matrices and along with the dimensions, okay, and then the degrees of freedom, that is the total number of effective unknowns which are present in each of the equations of the transformation matrices. Then what are the different properties that it preserves, okay, so that is also shown over here. And then finally just a representation of what this is. So all these, what it preserves, etc., is just the same as that of the 2D space. Okay, does anyone have any doubts so far? Okay. So we'll continue with the next topic, which is registration. Now, when I say image registration, okay, so what we are basically doing is we are finding the transformation that takes one data set to another. That means, let us say I have one image, okay, and I have another image, okay, and let me call this image as a source image and this image as the target image. Okay, so when I'm saying that I'm performing or I'm trying to do an image registration, what I'm doing is, what I'm assuming is that if I perform or if I do apply some kind of transformation, okay, on the source image, I get the target image. Okay, so I'm not taking two unrelated images or anything. What I'm doing is I'm taking images of the same scene. Okay, or maybe a little translated or a shifted scene. Like for example, if I'm taking a panoramic view, right? What I do is I keep taking multiple shots. Okay, while the camera is being moved. Okay, so that means that it is gradually it is like a translation operation that is happening there, right? So so what I'm saying is that the source and target image, okay, target images, it would be related by some kind of a transformation. Now this transformation can be a Euclidean transformation, it could be an affine transformation, it could be a projective transformation, okay, it could be any transformation here. And the basic problem of doing this image registration will boil down to finding what is this transformation that relates the source to the target, because only if you know what is this transformation that has happened can you would you be able to align these images together, or if it's for a 3D reconstruction you would be able to reconstruct the actual object from these images. So in all of the computer vision technique, most of the computer vision techniques, right, you will have to do an image registration. And image registration means basically trying to find out what is the transformation which can be applied on the source image in order to get the target image, or trying to find out this particular relationship between the source and the target. Now, when I talk about source and target, okay, in this case, I was talking about 2D to 2D transformations here, right? Now, the registration which can happen, it can also be between 3D to 3D, okay, or it can be from 2D to 3D, okay. So the transformations or the registration operations that can happen, okay, could be between the 2D to 2D dimensions, it could be 3D to 3D dimensions, it could be 2D to 3D dimensions. So we'll be discussing each of the case, separately. So first, what we'll be dealing with is the 2D to 2D transformations we have, okay. Now, now, why do you, or what are some of the applications of using their image registration? Okay, now one application of using the image registration is one example is, let's say you are taking some in the medical field. Okay, let's say you are taking, for example, let's say in a brain you have some tumor and you are trying to take the MRI. Okay, and let's say there are some other complications also. Okay, so you might be taking an MRI along with a PET scan, okay, or you might also be taking a CT scan, and you might want to register all these different images of the same human organ, okay, but which are taken using different imaging modalities, and then try to align them together, register them together. Okay, that is one example. Now, why we need that is just to get better details of that particular human organ that we are trying to trying to maybe operate on, or trying to diagnose if there is any disease. That could be one example. Another example is, let's say you have an MRI image of a particular patient's brain, okay, and if you're able to superimpose it on the real on the view of the real patient, okay, so there also it would help the surgeon with the surgical planning, okay, while the surgical planning in the sense, okay, even before the surgery as well as during the ongoing surgery, to see or to track how it has changed, etc. So those are just some examples in the medical field. And so let's say if you're taking satellite images, okay, and you want to kind of form a panoramic view, or kind of stitch the different images together, okay, to form an overall bigger picture of the particular landscape that you're looking at. In that case also you will need an image registration. So in that case, in that image registration, when you're going with image sticking, or the image mosaic as you call it, okay, not the whole image would be able or would align with itself, okay, but there would be a part of the image, okay, which would be very similar to the other one. So just like as I said, there might be a translation operation, okay, there might be a rotation operation or a scaling operation, etc. Okay, so there might be different kinds of transformation that may have happened, or which might be present when you are taking multiple shots of the scene. Okay, so the main aim of using these image transformations or the image registration is basically to try to find out what are these transformations, and then try to map, or try and find or align the source to the target. And this is used for various computer vision applications, and so it is important. The registration would form as one basic process when it comes to computer vision algorithms. Okay. Now, when we are studying about registration, there are different, types of registration. Okay. So when I take registration, I can say that this registration, it can be for rigid objects. Okay, so one type is the rigid objects. So what I mean by rigid objects is, so let's say that the objects which are present in the image, they do not change their shape, okay, after. So in the source, if I take the source and the target images, if I have a particular object, maybe the location has changed, maybe it has rotated, or etc., but the basic shape that you have here, or what you call it, it is the pose, okay, the position, or the basic shape, as in the basic shape over here, it does not change. So if that does not change, then what you can say is that it is a rigid object. okay, and the pose is constant. So this particular assumption in the rigid registration, okay, or techniques that deal with the registration techniques that deal with such rigid objects is what you call as the rigid registration, okay. And for rigid registration, okay, what we assume is the pose consistency, okay. Here the pose consistency, and what that means is that basically the pose of the object would remain the same throughout the different images which are to be registered or which are under consideration for registration. So that is one type. Another type of registration which you have is the deformable registration. So in the deformable registration, what we assume is that the object that we are considering, okay, it has changed its shape over the different images, or when we are taking the multiple shots of the same scene, the object tends to change its shape, okay. So such kind of registration or such kind of objects are called as deformable objects, and the registration techniques which deals with such kind of deformable objects are called as deformable registration techniques, okay. Now some examples of deformable objects or deformable objects is, for example, human organs. So when you're trying to, especially the heart or the lungs, when you're trying to take multiple images of the same, what we see is that, okay, since it is in motion, right, so the shape may not remain the same, okay. So just an example of deformable. So what we will be doing is we'll first be studying about the rigid registration, because it is actually easier to understand, because the it is under the assumption that the pose of the object remains the same. So there are not many factors to consider when we are going with when we are going about with a rigid registration, okay, because in rigid objects the shape remains unchanged, and so when you're trying to find the key points, okay, in order to find the correspondence between the two images, what we see is that the key points, it is easier to identify the key points because it remains the same, and it is easier to map these key points from the source to the target and to identify the transformation, okay. But in the case of deformable objects, it is a much more complex as compared to the rigid registration. Okay, so another case that you have is the 3D to 2D registration. Okay, so in this case, 3D might be the actual object that you have, and 2D might be some image of the 3D object. Okay, now how do you correspond between points in the 3D object to the corresponding points in the 2D image of the same object? Okay, is this kind of transformation or this kind of registration technique is also a third category which we'll be studying about. Okay, just give me a minute. Okay, now coming back to registering the rigid objects. Okay, so first we'll be seeing some of the techniques by which we can go about with rigid registration. So in the rigid registration, basically what we assume is that the shape of the object does not change, right? Now let's look at some mathematical equations or mathematical modeling for this particular problem. So let's say that xi is the set of points, okay, which are present in the source image, and yj are the set of points which are present in the target set. Okay, so instead of saying it as image, let me call it as a set over here. So it could be a 2D image, it could be a 3D space, etc. Okay, so given a source set and a target set and the different points which are present, what we are assuming is that since it is a rigid these are rigid registration techniques, okay, the techniques or the transformations that is involved is rotation, translation, and scaling operations. So that means if I take the source set, Okay, and if I do some kind of combination of the rotation, translation, and scaling, I get the target image. So this is my assumption. And what I'm trying to do is, so let's say I have a set of points xi over here, and I have a set of points yi over here. If I'm able to find the correspondence of these set of points which with each other, okay, so these would be my known quantities over here. What I need to do is I need to find out this transformation. That is, I need to find out the combination of rotation, translation, and scaling, okay, which when applied to the source image or to these points would give me this yi over here. Okay, so that is the basic structure of the problem. That is trying to find out what is the rotation, translation, and scaling operations, okay, that could map between xi and yi. So let us, in that case, the first thing that we require to do over here is we need to find out what is the correspondence between these two points, that is the points in the source image as well as the target image, right? That is, which point on the target image is a transformed version of which point in the source image, right? So trying to find that is what you call as finding the correspondence between the two points, okay, and this correspondence is what we can denote as ci. So here whenever in the equations you see the ci, what that means is it is basically the mapping or the correspondence points that you have, okay, what is the correspondence between xi and yi, or the different points in xi and yi. Now what we do is, in order to find out these rotation, translation, and scaling operations, or the values of these, okay, which would best fit, okay, the source and the target, which means what are the values of r, t, and s, which when applied on s will give me the target image, okay. So trying to find that out, we can formulate that as a minimization problem. Okay, it's a least square minimization problem. So what that means is I try to apply the transformation, okay, on the source image, and that transformed. So this is basically my transformed source image. So from the transformed source image, I try to subtract, okay, the corresponding points in the target image. So what ci means is, yci is basically the points, okay, which correspond, the points in the target space which correspond to the points xi is basically the points in the source image or the source set, right? And yi are basically the points in the target set. Yci are the points which correspond to the points xi. Okay, so if I apply the transformation in the source image, okay, that is this term over here, and then try to subtract or try to find how different that is from the corresponding points in the target image, okay, so what I get is basically an error factor over here, right? So what I do is that difference, I take the square of that and then I take the mean or the average of that. Okay, so that gives me a least square solution. So what I'm trying to do is this error function, which I'm trying to calculate, I'm trying to find out what is the least minimum value which is possible. Okay, that means as I'm trying to for different values of r, by varying the values r in the sense theta, okay, because theta is the variable over here, right? So by changing the values of theta, s, and t, okay, I'm trying to find out what is the minimum or least possible value of this error function which I can obtain. Okay, that is what you call as a minimization problem. You're trying to find the minimum possible value out of these in different iterations. Okay, and for each iterations, I try to modify the value of s, theta, and t such that it will drive the minimum value to the converging or the least minimum value as possible. Now, while you do that, when you are iteratively doing that, okay, so what you're expecting is if 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 this target image, okay, is a true transformed image of the source image, okay, that is, if the target image is a true transformed version of the source image, I can say this value would be equal to 0. I mean, if it should be exactly same, or if you need to find out the exact transformation over here, then it should be equal to 0. Okay. But you see that in practical cases, you will not get it as exactly equal to 0, because of various reasons. One reason may be the presence of noise, which are, or any other artifacts which are present in the target image. Okay, so therefore we may not be able to exactly apply the same what is it, transformations over here to get the exact image. Okay, so there might be some noise which are present, because if you think of this, the source image is taken at a point of time, or at a time instant t, which is the target image, it is taken at another time instant, right? So there might be some noise or some kind of artifact which can happen, okay, while taking these multiple shots or multiple images. That is one thing. That is one thing why you cannot, you may not be able to get the exact transformation values over here to connect the, or to relate, or to align the source with that of the target. Now another reason is, let's say you have these points xi and yi, and these are not points which are manually detected. Okay, these are points which are resulting from some other image processing techniques, let's say. Okay, so that is, for example, if you remember, we had already learned about the key points. Okay, we learned about the Sept key points. We also learned about gradient operations, about edge operators, etc. Right? So when you're trying to find these key points or features of interest in each image, right, you can find it by using different image processing techniques. Either you can apply some kind of key point detection techniques, or maybe you can apply some kind of you can detect some kind of features in the image, okay, to take it as a point of interest. Or maybe you can use the gradient operation, or maybe you can use the edge operators or something, okay, and from there you can calculate the points, right? So when you're using these to find the points, okay, we may not get points that exactly correspond with each other in the source and the target. Okay, so that means even if I'm using some kind of image processing techniques to find these points, so if these points have resulted from some kind of previous or prior image processing techniques, okay, then there might be some errors which are creeped in, okay, from as a result of those techniques. So therefore, after doing that, when you're trying to find the correspondence, okay, there might be, you may not get exactly the same correspondence, or you might not get exact values for r, t and s, for which you will get this value exactly 0. Okay, so that is why we are focusing it on a minimization problem, where we say that we are trying to minimize this error function to the least possible value which is possible. Okay, the least value, or when I say least value which is possible, what I'm saying is, or another technical term that we use is still convergence. Okay, that means convergence is the point where if you are still changing the values of s, r and t, okay, you see that the minimum, the least minimum value which you get would, or the error function would remain the same. So after iterative, or after the last few iterations, if you see that the error function does not go below further, then you can say that it has converged and you can stop over there. So the minimum possible value which you get, okay, corresponding to that, what are the values of s, theta and t, okay, you can say that that is the particular transformation which can be applied to the source image to get the target image. So this is the least square solution problem. Okay. Now, so as I said earlier, we cannot say for certain that I have found all the xi and yci correctly. That means, let's again saying this is a source image and this is, let's say, the target image, and I have some points here, I have some points over here, right? And then what I'm trying to do is I'm trying to find this particular transformation. What is the transformation that took me from here to say? So when I say transformation, In this case, since it is rigid transformation, what I'm assuming is scaling factor, the rotation theta, and here the translation operation, so it is t. Okay, so what is this combination of s, theta, and t, which can give me an exact match or the best match possible with the source and the target, is what we were discussing in the previous case on the previous slide, right? Now, as I said earlier, due to the noise which are present, or because due to some not being able to find the exact key points or exact corresponding key points, there may not be a perfect correspondence between each of those. Okay, so since I cannot say with 100% confidence that I have found all the corresponding points correctly over here, okay, what I can do is another method or another approach which I can do is, instead of just taking source and target, I am also assuming an intermediate set. Okay, I'm not going to call it image, let me call it as a set. I'm going to assume an intermediate set G here. Okay, so in this G, what I'm assuming is that if I'm applying the operations, that is the scaling operation, the rotation operation, and the translation operation, if I'm applying these operations on the scale on the source image, okay, I get this image over here, the transformed image G, right? Now this transformed image G, what I do is, next I try to calculate what is the similarity between this G and T. Okay, so G is basically the transformed version of the source. Okay, and then after getting this transformed version, I try to calculate how much similar is G and T. Okay, and based on the similarity, I put a particular score for that. Right, now what I do is, until and unless, so what I'm trying to do is, I'm trying to ensure that the similarity between G and T is as high as possible. Okay, so to get it as high as possible over here, what I do is I calculate my S, theta, and T. So when I say similarity must be high, what I mean is that the error function between G and T is tried to be reduced. Okay, so what I can do is I can introduce this term over G over here, right? And G is basically the transformed version of S. And what I'm assuming is that even though G does not exactly coincide with all the points in T, that is a target, I should at least assume that it should lie as close as possible to the points in T. So whatever points you have in T, right, this the points which are there in G should lie as close as possible. Okay, so that is the assumption that I make here, and that is what I work with for this particular approach that we'll be studying. So again, for doing this, we can go with two approaches. First approach is, we can assume, or what we do is we try to estimate the correspondences and then estimate the transformation given a correspondence and repeating. So it's like a repetitive process. Okay, so that means, as I said, we do not make the assumption that there is a one-to-one correspondence between all the points in the source and the target, or basically the G image or G set and T. Okay, there might be some points which may be, which may be present as outliers. Okay, so here, in such a case, when it is not exactly the same, what happens is the least square sum that you are getting would not be equal to 0. It would just be a low value, as I said, right? So what you can do is that you can go with two approaches to find the transformation values, that is S, theta, and T, using the G and T. Okay, that is the these two, G and T. You're trying to find out what could be these values of S, theta, and T. So the two approaches that we use, one approach is where you find points in G over here which are very close to T. Okay, and then you use a least square minimization, or a least square sum, okay, to minimize this error over here. Okay, so the least square sum would be in terms of S, theta, and T, right? So we try to keep changing this transformation over here iteratively in such a way that this G and this T over here, okay, the difference here or the error between G and T keeps reducing with each iteration, okay, and it would keep reducing and till it gets the least minimum value or the least minimum error which is possible. You keep iterating over S theta and T, and then so that is one approach where you do, okay. And what we are assuming, as I said earlier, is that there are points in G, okay, and there are key points or interest points in T, and we are assuming that these points in G should lie as close as possible to the points in T, right? Now, another approach is, instead of taking just the points or the interest points, I can also take a group of points or maybe a line segment, etc. So that means instead of going for a one-to-one, point-to-point correspondence, I can also go with a group of points correspondence. That is, if I take a line segment, right, that would be a group of points, right? If I take let's say along with the line segment, I also consider a pair of points, let's say, then that combination together can be used to find out this transformation. So this is what you call as basically the frame bearing groups, which we will see later. Okay, so what you need to remember is the approaches which we can take is either you can go with a one-to-one, point-to-point correspondence, okay, or another approach is where you consider a group of points together and try to register them, or trying to find the minimum least distance value, or the closest value as possible. Okay, and one famous method which can be a very popular method which can be used for finding this is the iterated closest points, or it's also abbreviated as ICP, the iterated closest points. Okay, so in the iterated closest points, what we do is, okay, we try to find out which are the closest points which is present between J and T, okay, and then we iteratively try to modify the values of the transformations, okay, in such a way that we get the closest points as possible. So let's say, okay, so this is the algorithm over here. So let's say we start off with an initial estimate, okay. So we take an initial estimate of this S theta and T, basically the scaling, rotation and translation operations, okay. And then using this estimate, we try to find out G, right? So from the source, I'm trying to find out this G using, so I have an initial estimate over here, right? Now, using this estimates, after, what we do is, we first transform all the points in S, okay, to G using this initial estimate, okay, and we try to find the correspondence, okay, between each of the point in G with respect to the points in T. Okay, and this particular correspondence that we try to find between these two, we can call it as CI, as I've told earlier, right? So each time I does a transformation over here, okay, I also try to find out what is the correspondence here, okay, and then after I find the correspondence, I have a value for the correspondence, and then what I do is I try to vary the value of S theta and T over different iterations. So when I'm trying to minimize the least square solution, right, or the least square minimization problem over here, okay, what I'm trying to do is I'm trying to minimize the error between these two, okay, by varying the values of S theta and T over the iterations. And how long would I keep doing these iterations? I keep iterating, okay, so each time I get a new estimate, okay, I again keep iterating it, okay, I again use that for the least square minimization, and I repeat it until I get the minimum possible value for the error function. So that's why it's called as a least square minimization problem, okay, and that is when you say that it would converge. So converge is basically, what that means is, it does not go any low further, okay, or even if I change the values of these S theta and T, okay, it does not go down any further, right? Now, one thing you have to remember is here when you're calculating the initial estimate, okay, this initial estimate can be calculated as a result of any other, prior operations or so, okay. But whatever is the initial estimate that we calculate or that we are assuming or that we are taking, okay, it would depend upon this initial estimate on how fast you reach the converged value or how fast you reach the let me call it as the optimal solution. Okay, so if the initial estimate is close to the actual value, okay, it lies somewhere near, or these values of s theta and t is somewhere close to the actual transformation values of s theta and t, then I can say that the convergence can happen within a few iterations. But if the value of s theta and t is very much further away, or if there is a large difference between the values of s theta and t, or the initial estimate with that of the actual values of the transformation, then what happens is you might need a lot many iterations to actually reach the optimal solution. Okay, so the convergence over here, the speed of convergence over here would depend upon what is the initial estimate that we are considering over here. So that's again another point that you need to note. Okay, so this is just an illustration of how the iterated closest points work. So let us assume that this set of red points that you see here is the source set, okay? And the set of blue dots that you see over here is the target set, okay? So in this figure, when you see, what we see is that you can see an elliptical like a point. If you look at all these point groups with the group of points over here, it gives us a resemblance of an elliptical shape. Here also you get an elliptical shape, but here what we see is that there are some points, okay, which actually is not belonging to this particular distribution over here, right? So this set of points, you can call it as outliers, because this is from visually when you're having a look at it, we can easily say that these points do not really belong to this particular distribution or this particular model, right? And therefore you can call these as the outliers. Anyway, so let's say you have the source set, okay, and the target set, and what you're trying to do is you're trying to find the correspondence between these two, right? So first, in the iterated closest point, what we do is first you find an initial estimate, right? So in this case, the initial estimate is found using the PCA analysis, principal component analysis. So basically, it's just like taking the axis of these two and then trying to do rotation and translation in order to try to combine them together. Okay, and since it is PCA, we take the principal components and then try to align them. Okay, so not going into the details of that. So you can use any algorithm over here in place of PCA also to find the initial estimate. So here we have taken the PCA, or in this particular image, the PCA transform has been used in order to estimate the initial transformation. Okay, and after applying that, what we have got, this position of the red points which we see over here, okay, is the initial estimate. Okay, after doing the PCA, the initial estimate that we have got. Now, after finding this initial estimate, what we do is, okay, we find, or this ICP, and this is abbreviated as ICP. So the ICP algorithm, what it does is, it will try to find out what is the closest points. Okay, so for each of the points in the target, okay, what is the closest point in the source is determined. So those are these lines over here. These lines over here represents what are the closest points. And how do you calculate the closest points? Basically, it uses some kind of a distance measure to calculate what are these distance between the different points, and then try to see what is the closest of these. Okay, so that means, let's say I have a point over here. Now if I consider in this neighborhood what are the different points, I might see 1, 2, 3 points. So in these three, I try to calculate what is the distance. Okay, here I have a distance. Here I calculate what is the distance. Here I calculate what is the distance. Out of this, I try to find out the one with the least distance here. So I found that this is the point with least distance, and then I take, okay, so this is the closest point which is available for this particular point in the target. Okay. So like that, for all the points in the target, the ICP finds out what is the closest point using distance measures. Say, like for example, if it's a Euclidean distance, it might use Euclidean distance to measure the closest point. Okay. Now, what happens is, so after this, okay, we have found the closest point. Now, what we try to do is the error calculation over here would be in how much is the difference between these points in the target as well as the source image over here, okay, or the source in the sense the transformed image over here, transformed and the target image. So after every iteration, the values of s, theta and t is differed, okay? And for different values of s, theta and t, what happens is you see that this starts getting closer and closer. So the aim of the least square minimization problem is to try to reduce these distance values over between each of the corresponding points, right? And this keeps reducing. So after every iteration, that the distance keeps reducing, okay, and accordingly that forms a new estimate for the s, r and theta, and this keeps on going. So finally, after 10 iterations for this particular example, what we say is we say that the source as well as the target set over here, okay, they have somehow aligned with each other, right? So what we are doing is right now, as we see, there are points which are unused over here. Also, the outliers are still present over here, right? So what the ICP does is each time or for each iteration, it tries to find out what is the closest point, and it will try to minimize this distance which is present over here, okay? And by minimizing that, we try to find out a new estimate for the transformations, and for every iterations, this keeps repeating, and finally what you get would be the aligned source and target set. Okay, so if it is a set, you can think of it as a 2D image also, okay, where you're trying to do a rigid registration of the two images. If it's an object, you can take it as an object. Now let's say this is just an example in the 3D space where we are assuming the points are present, not just in a plane as previous case. This is in the 3D view. Okay, so you have it this way. Okay, 98. Okay, so you have it this way where this is a 3D space, right? Now you can consider the points as a 3D point cloud. You call it as a cloud because now you have another dimension also, right? So if you look at it as a 3D point cloud, and the blue representing the target and the S representing the source. Okay, so this is just an example on how with each, so this is the initial estimate after PCA, where you see that it have somehow coincided, but still there are regions, you know, which is not exactly corresponding, or which is not which is lying far away from the corresponding points. And then after different iterations, we say that it has somehow you know, tried to align with each other. Okay, so this is an example of a femur bone which is represented in the form of a 3D point cloud. Okay, so that is basically how ICP works. Okay, and you can also you know, improvise on the ICP problem by you know, adding some more constraints or some more restrictions. Like for example, when you're trying to find out what is the distance between you know, two different points. Okay, let's say you have closest point here, then some of the distributions had like this. Okay, so we can kind of put a threshold where you say that, okay, if the distance between 2 points is beyond particular threshold, let's not, you know, consider that for the next iteration, and so on. So what you're doing there is you're trying to reduce on how many points are might be contributing much more to the error. Okay, and we are focusing more on points which are close together, so that it is easier to come to the convergence. Okay, so that is one modification that can be done, or one change that could be done, where you discard the points which are too far away. Then we can also use better algorithms also can be used. Okay, maybe for calculating distance you can use different other distance measures, or maybe you can keep use some other method for finding the correspondence, etc. Or instead of the least square estimation, you can use some other estimation functions or algorithms. Okay, and so on. So there are various ways by which the ICP algorithm can be further modified. So this was the okay. It's almost 5:30 now. Fine. Okay, I'll just continue with this. I'll just take 5 minutes more. Okay, so in the previous case, what we were looking was a point-to-point correspondence, right? So instead of a point-to-point correspondence discussed earlier, instead of point to point, you can also go with group of points. Okay, you can look for correspondence of group of points with another group of points too. Okay, so for that, when I say group of points, okay, it can be line segments, okay, it can be corners. That means you're using other primitives also to use, or it can be some features like blob-like features which are present. So all these can also be used as a group of points in order to find the correspondence, rather than just sticking to a point-to-point correspondence alone. Okay, a group of points can be used, and using such collection of primitives, okay, in order to find the transformation, you can call it as a frame bearing group. Okay, and these are some examples, okay, of the frame bearing group. That is, these are examples for 2D to 2D transformation. So if I'm doing a 2D to 2D transformation, okay, what are frame bearing groups means what are the different combinations, okay, which can be used in order to determine this particular transformation. Like for an example, we know that if it is just a rigid transformation, okay, so Euclidean transformation, in the sense it involves only rotation and translation. Okay, so if you can use just 2 points, okay, you will be able to find this transformation. Or if you're using a line along with a point, okay, then a line and a point pair can also be used for finding this particular transformation. So these set of combinations that you use is basically what you call as a frame bearing groups. Okay, and this combination can be used. Like for example, if I have a particular line, okay, along with a point, okay, which is given like this, and let's say in the transform image I have it something like this. This pair which I use, okay, together it can be used to calculate or find what is the transformation that has happened between these two images, or these two objects where the line as well as the point is present. Now let's say in the case of a rigid and scale operation, okay, in the case of a rigid and scale operation, either I can use 2 points, or I can use a point and a line and a point which is not present in the line. If it is the affine transformation, I can use three non-collinear points. Okay, three non-collinear points to just find out what is the affine transformation that has happened. So this is the case of 2D to 2D registration. In the case of 3D to 3D registration, you have one more dimension, right? So it is slightly different. What you have is for the rigid or the Euclidean transformation, you say that, for example, you need 3 points, not 2 points. Earlier it was 2 points. Here, if you can just find 3 points, that would be well and good. or you can use a line with a point of the line, okay, that is not present on the line, or you can use two intersecting lines. Okay, in the case of rigid scale, accordingly you have another set of frame bearing groups that can be used. In the case of affine, okay, you need at least 4 points. In the previous case it was 3 non-collinear points. Here you have 4 non-collinear points, etc. So these are what you call as frame bearing groups. And as I said earlier, in frame bearing groups, what we are doing is we are trying to find the correspondence between a group of points in the source image and the target image, rather than going for a point-to-point, exact point-to-point correspondence, because it is difficult to find such an exact point-to-point correspondence when you're taking images, as I said, because of the presence of noise, or because of the because it is coming as a result of other image processing techniques, etc. Finding an exact point-to-point correspondence is difficult, and so you can also go with a frame bearing group in order to, that is a group of points for the for calculating the correspondence. Okay, so I'll stop over here. If you have any doubts, you can ask me now.